Good day, everyone. Thank you all for joining us today for our seminar. Please let us wait 5 more minutes for all of the other participants to join, and we will begin shortly. Thank you for your time. Hello, everyone. Thank you all for joining us today. My name is Alexi, and today we shall be speaking about vacuum drying ovens. Now, as it is tradition with all of our seminars, you can ask questions in the chat. I repeat, you can ask questions in the chat. We will answer them and when we have time. If you wish to have a certificate of participation, please message Oksana. Write your name, the name of your company, and your email. I repeat, please message Oksana, write your full name, the name of your company, as well as your email. We will speak why the vacuum drying ovens are needed and what they serve for. Our lecture will consist of two parts. In the first part, we will provide theoretical information. In the second part, we will showcase our developments in practice. We will show their joint action and clearly illustrate to you the operation of this equipment. My colleague Tim will be taking over that part. All the equipment that we are going to discuss and show today is manufactured by GlobeCore. Our experience is based on many years of the company's operations, as well as on direct cooperating and customer feedback. So, vacuum drying ovens are used for thermal drying of the transformer's detachable section, is what a short answer would be. However, there are plenty of drying technologies for various applications. Only carefully dried insulating materials ensure a fault-free functioning of high power and high voltage electrical products and slow down the aging process. Materials used for insulation of transformers, such as transformer oils and cellulose, tend to become saturated with moisture. Therefore, it is very important to reduce the humidity to a minimum for ensuring the resistance to breakdowns and the shape stability. I also want to ask all of you if you can hear me well, if you can see the slides. Please write a plus in the chat if you can hear me well and see our demonstration of our presentation, please. So, the process of drying the insulation of power transformers is one of the major and most important processes because the state of the insulation during operation primarily determines the service life of a power transformer as a whole. The main material for the insulation of windings is cellulose, as the most susceptible to aging. Ensuring the reliability and good quality of insulation is a constant challenge for manufacturers of electrical equipment. The first objective to be achieved is certainly to impart the insulation with sufficient dielectric strength so as it can withstand the required tests. Added to this is the intention to reduce the aging rate of insulation while operating, as well as to ensure the ability of the windings to withstand electrical and electrodynamic effects. Paper oil insulation in transformers is designed for reliable operation as long as it has high insulating properties, such as resistance, dielectric strength, electrical capacity, and low dielectric losses. These factors depend first and foremost on the humidity of insulation. Due to its capillary structure, paper insulation is highly hygroscopic. Transformer oil is somewhat less hygroscopic. Therefore, after outdoor exposure, the active section becomes humid, even as it is impregnated with oil. Moreover, in old transformers without air dryers, the insulation becomes humid during long-term operation. If windings are made again, their insulation also features an increased humidity. The purpose of drying is to remove moisture from a transformer's solid insulation that primarily contains fibrous materials, such as electric-grade cardboard, paper, or wood. These materials absorb moisture from the environment, which sharply deteriorates their insulating properties. Drying of active sections is used in order to free the paper insulation of moisture and to bring its properties to the established standards. Drying is based on the thermodynamic process. The efficiency of processing the transformer's active section should be evaluated, not only in terms of attaining a sufficient dielectric strength during tests, but also in terms of extending the service life and enhancing the operational reliability. The cost of processing is determined by its duration and quality, as well as by the installation characteristics to be attained. The ovens are used in manufacture and repair of transformers. The purpose of this machine is to remove moisture from electromechanical equipment. This equipment is used at transformer manufacture and repair facilities. In the process of manufacturing, the main function is drying or preparation of a winding, maximizing the insulation characteristics prior to installation in the transformer and filling it with oil. Now, that was a lot for all of you. And again, if you have any questions regarding this, feel free to write them in the chat. We will answer them. So, under operating conditions, moisture and gases can move from the oil and reach critical values in the most stressed spots of the winding. Alternate heating and cooling of the transformer under certain conditions is dangerous for its installation. For example, the transformer operated for some time at a low temperature and a considerable amount of water was absorbed by the solid insulation. With a sharp increase in temperature under load, the water will be redistributed and will pass from paper to oil. If the insulation is of solid type, the water cannot be released quickly, and the paper will be in a state of local oversaturation. There is a risk of thermal breakdown at a high temperature. Or, over a short period of time, a considerable amount of water will turn into oil, which will have a high moisture content. At high temperature, it may not be too dangerous unless the oil is saturated with water. But if the load has decreased and the oil has cooled quickly, it will be oversaturated with water and an emulsion will form. This state is extremely dangerous because the dielectric strength sharply drops. Moreover, in this case, the surface of the solid insulation may be locally moistened, which is also dangerous. The service life of the transformer insulation system is determined by the service life of the paper insulation. When the insulation is in its normal state, the polymerization degree ranges within 800 to 600 units. The lifetime of the windings paper insulation is considered to be exhausted when the polymerization degree of the paper decreases to 250 units or less, as you can see on the graph before you. The experience of operating entities shows that a polymerization factor of approximately 200 indicates unusable insulation. New insulation has a polymerization factor of 1000 to 1200. When exposed to a number of elements such as thermal, chemical, and others, the insulation undergoes aging, a process that deteriorates its characteristics. Having no significant impact on electrical properties, aging drastically manifests itself as a change in mechanical characteristics. In order to evaluate the state of insulation, one should determine its polymerization degree. So, why we were so boring regarding all of this polymerization is clearly shown on this slide. Hydrolysis and pyrolysis of cellulose leads to its depolymerization. Both mechanisms form furan acids to release and distinctive gases such as CO and CO2 to evolve. The main factors for accelerated aging of insulation include elevated temperature, increased humidity of the windings insulation, oxygen, and oil aging products. A significant factor in oil oxidization, even with a low oxygen content, is the increased contents of metals, especially copper, in oil. Those who want a more detailed explanation of the degradation caused by pyrolysis, hydrolysis, and oxidization can find information in the chat if you wish to know it. For now, let us move on. The information given in the previous slides helps us to understand how to remove moisture from the transformer windings. We can conclude that the moisture contained in the transformer winding serves as a catalyst to start the paper insulation aging process, and also serves as a parameter to start other concurrent processes inside the transformer. A thermodynamic drying process is used to remove moisture from the insulation. The thermodynamic drying process is based on using the phenomena of moisture conductivity and diffusion of vapor from the heated surface of the insulation. The drying process comprises the following stages: convection, a heating of the insulation, movement of moisture from the inner layers of the insulation to the outside, and vapor formation and vapor diffusion from the surface of the insulation into the surrounding space. And I repeat, if any of you have any questions, you can ask them in the chat. And if you wish to receive a certificate of participation, please message Oksana. Write your full name, the name of your company, and your email. This is to those participants that just have joined us. I repeat, message Oksana privately, write your full name, the name of your company, and your email. Now let us continue. Inside the insulation, moisture moves in the form of vapor from the spots with a higher content to the spots with a lower content, and from the spots with a higher temperature to the spots with a lower temperature. Therefore, in order to accelerate the movement of moisture to the surface of the insulation, it is necessary to ensure fast and good heating of the entire active section of the transformer. In order to speed up drying, the maximum allowable temperature of 100 to 110 degrees Celsius for paper fiber insulation and vacuuming are applied. Vacuum serves to reduce the vapor formation temperature, to speed up drying, and to remove water vapor from the drying unit, as well as to maintain the relative humidity of air inside this unit at a low level. The thermodynamic drying process resides in the fact that the insulation heats up and moisture moves from its internal pores to the surface, and then to the environment. The higher the heating temperature of the insulation, the greater the difference between the partial pressures in the adjacent layers of the insulation, and the more intensively the drying process occurs. For this very reason, the insulation is heated to 100 to 105 degrees Celsius. On the other hand, pressure is effectively reduced in the surrounding space. For example, a vacuum is created in the drying oven. The lower the vapor pressure in the environment, the more intensively moisture is removed from the surface of the material. Therefore, in order to speed up drying, it is necessary to reduce the vapor pressure in the environment and to increase the vapor pressure on the surface of the material. The former is achieved by creating a vacuum in the drying oven. The latter is achieved by heating the active section of the transformer. Various methods of drying the transformer insulation are used at transformer factories, at electrical repair facilities, as well as in electrical grids and systems. Choose the most suitable drying method for this facility, division, or workshop based on its production capacity, as well as taking into consideration the range of transformers under repair. Based on our experience, in the process of thermodynamic drying, one of the main parameters affecting the rate and the quality of drying is the heating method. Types of vacuum ovens are primarily made in accordance with types of heating. Choosing the heating method affects the rate and quality of drying. There are three main methods of heating the insulation of the active section of the transformer during vacuum heat processing, with hot oil as a heat carrier or with hot air, HAV, with solvent vapors, VPD, or low-frequency heating, LFH. The method of heating with oil and electric heating by means of electric heaters are two similar methods. The main difference is how heat is supplied to the chamber. It is obvious that heating by means of electric heaters is easier to produce and maintain because it uses no additional system of hot air carrier circulation in its design. The transfer of heat using such methods is facilitated by heating the space inside the chamber. The next method of heating is with solvent vapors. It is completely different and more complicated method of drying the insulation. Transfer of heat to the winding is facilitated by spraying a heated solvent in the chamber, and this heated solvent serves as a heat carrier. Moreover, when repairing the used windings in the course of drying, the hot solvent displaces old oil from the winding. This method is good, but the complexity of maintenance and production affects its expendency. The same goes for operation with the use of explosive hydrocarbons. Now, low-frequency heating. This method resides in the heating the actual winding by applying low-frequency currents to the very winding itself. The advantage of this method is that the actual winding is directly heated, which explicitly affects the energy efficiency and the cost effectiveness, which is something that all of you are interested. So, when selecting the drying mode, it is necessary to proceed from a rational combination of the following: the required quality of dryable material determined by the standard, a class of drying models that ensures the necessary quality of drying at the specified duration of the process, and the chamber design capable of drying the material according to a certain quality class, without exceeding the mode-specific duration. In addition to the technological features of using one mode or another, the economic aspects, such as the cost effectiveness of using the modes of different intensity, should be considered. In order to facilitate the movement of moisture to the surface of materials, it is necessary to ensure fast and good heating of the entire active section of the transformer. This graphic chart shows a comparable table for the methods of drying the insulation in vacuum ovens. HAV is the method of drying through hot air blowing followed by a cycle of vacuuming. VPD is a method of drying by means of solvent vapors, and LFH is a method of drying through low-frequency currents. The HAV method requires expenditures in terms of processing time and energy consumption. Considering that the hot air blowing unit can reach a power level over 100 kilowatts per hour, takes much more time compared to advanced methods of drying. We deal with great costs considering the fact that the final quality of drying is much worse than in the events of more advanced methods. With regard to the comparison of VPD and LFH, we see a reverse trend of expenditures in terms of processing time and energy consumption, which is 3 to 5 times less. However, they require more maintenance and financial investments. In a long term, the difference will be noticeable and the LFH units show their efficiency. However, considering that transformer downtime is an expensive process, it is possible to conclude that it is more effective to use VPD and LFH systems, which will save our time and the insulation will be as good as new according to the humidity readings after drying. The VPD method requires large investments associated with purchase and maintenance of this equipment. Moreover, as we said before, the actual process is quite complex and requires trained personnel. This method is efficient, but very complex and inexpedient compared to simpler and not less efficient methods. Considering all of our factors, we can conclude that the most efficient method is LFH, the HAV hot air drying method, in combination with the LFH method of drying through low-frequency currents, will deliver a good result as the winding is heated from the inside and outside. The combination of these methods is the most efficient and economically viable. So, compared to conventional drying units with hot air circulation, the advantages of using a vacuum are clearly evident. The drying time is shortened nearly by half. Thermal vacuum drying equipment with hot air circulation is used for various applications and facilitates achieving the excellent drying results. Electric heating by means of electric heating plates can also be used for small-sized autoclaves. Advanced technologies of this equipment ensure excellent drying results. Thus, the drying time is shortened nearly by half compared to drying without a vacuum. This is achieved by means of optimized and uniform heat distribution using fans and air deflectors, as well as by fully fledged heating of the autoclave. Heating inside the chamber occurs due to the electrical heating elements located on the side walls of the chamber. Due to the direct heating of the medium, the temperature in the chamber rises rather quickly, which makes it possible to shorten the drying time. In such chambers, the heating elements are covered with panels, and the uniform distribution of heat occurs due to the installed centrifugal fans, with the help of which the internal convection of hot air is carried out during the heating cycle. That makes it possible to evenly warm up the entire winding over the entire area. In order to evacuate the vapors during the heating cycle, a centrifugal fan is used for blowing the vapors out of the chamber to avoid moisture condensation on the chamber walls and the winding itself. This method is the most versatile. One of the big advantages of this method is the possibility of combining it with other types of heating, which will give it a big plus in the speed and the quality of drying of the windings. And now for my favorite part, low-frequency heating. Low-frequency heating is quite a unique process for drying the transformer insulation by injecting a regulated low-frequency current into its high-voltage windings. This system works better and faster than traditional methods. It can reduce energy costs by up to 2 times and greatly speeds up the operating process. In our practical experience, the application of this drying method in combination with other traditional methods of drying the insulation delivers the best possible option as a final product. The equipment with direct electric heating through low-frequency currents is designed for fully automated manufacturing of transformers of various sizes and types, in medium and large batches. High flexibility in loading the batches of transformers is unique and essential, especially in the field of distribution transformers. The shortest process time is achieved owing to concurrent heating and vacuum drying. The whole process takes place at a low vacuum, which results in considerable improvement of the drying quality and in reduction of the insulating material depolymerization compared to conventional drying methods. Now, as I wanted to remind all of you again, you can ask questions in the chat. We will answer them. Don't be afraid. As well as those of you who have just joined us, please, if you wish to have a certificate of participation, privately message Oksana. Write your full name, the name of your company, and your email. Now, let's get to the meat of the bones of the operating principle of the LFH method. The LFH process allows the high voltage and low voltage windings of the transformer to be evenly heated from this side by supplying low frequency and low voltage current into the high voltage windings, while the low voltage windings are short-circuited. At low frequency and low resistance, there arise no high voltage problems, and magnetic bond creates a well-controlled current in the low voltage winding. During the process, the high and low voltage transformer windings are heated to a typical drying temperature of 110 to 120 degrees Celsius, as in the solvent vapor drying process. In order to monitor the drying process, and especially the winding temperature, special monitoring methods should be used to prevent the formation of overheated areas and, as a result, damage to the insulation. In order to continuously monitor currents, voltages, resistances, and vacuum level, this system uses unique control and monitoring arrangements. The system determines the temperatures of high voltage and low voltage windings with high precision and allows heating the high voltage windings independently if the temperature thereof is lower than the temperature of the low voltage windings. Monitoring the vacuum level is necessary because the breakdown voltage is reduced in vacuum, and continuous monitoring of the temperatures of how high voltage and low voltage windings allows optimizing the drying process. So let's figure out what we need to operate a transformer. Each transformer has a data plate. We will need to find the parameters required. Based on the rating plate data, we shall enter the rated current of the transformer's primary winding into the settings of the low-frequency heating system. We shall specify in the settings transformer with or without oil. We shall set the process frequency, normally 1 Hertz, and the drying process time in hours. The unit calculates by itself the heating current, the resistance, and temperature of the windings. The inverter ensures electric current flow and heating. As we mentioned above, the transformer is disconnected from the power line and the power leads of the inverter, and the measuring circuits of the ohmmeter are connected to the high voltage winding of the transformer. The low voltage winding is short-circuited due to magnetic bond and low frequency. The magnetic circuit is saturated and the windings are heated. The inverter periodically shuts off. The resistance and temperature of the heated windings are checked, and the transformer tank and the transformer oil temperatures are continuously monitored. A hot air drying vacuum chamber in combination with the LFH system will yield the result. Since this method of drying the distribution transformers ensures minimum energy costs and offers other advantages, such as accelerated drying process, high capacity, and easy control. Hot air vacuum drying methods are widely used for drying of small transformers, so there is an enormous potential to upgrade such systems with LFH. A traditional hot air drying system would take at least twice as long to complete the drying process. If a small dryer with hot air circulation consumes 50 kilowatts and operates for 80 hours, the total energy consumption for drying a small transformer takes 4,000 kilowatts per hour. If the drying time is reduced by 15%, 50, that's 50, the energy saving in the event of drying one transformer by the LFH method will amount to at least 2,000 kilowatts per hour. This is due to the fact that two heating methods are combined when the windings are heated. As a result, the winding is warmed up quickly and evenly from the inside and outside. Moreover, during the vacuuming cycle, heat is removed from the winding due to moisture evaporation. After that, the windings should be reheated. By means of the LFH module, we can keep the temperature of the winding longer during vacuuming, since in our case, the winding itself is a source of heat. Owing to this, no inclusion of additional heating system is required. As I have mentioned previously, please wait for our second part, where my colleague Tim will be showing off the practical side of such methods. Now, we are going to compare one of our HAV windings drying systems and HAV in combination with the LFH system. We made this comparison so that we could see the efficiency of the methods and their combination. Let's calculate the time spent and the total consumption of power required for drying the same type of windings using different methods. These processes are considered time-consuming, therefore they proceed slowly, and it is impossible to see the efficiency in dynamics. We can check the efficiency and quality upon completion of the process, having calculated the time and resources spent. Therefore, at our request, the customer provided us with time and energy efficiency data after purchasing our HAV plus LFH equipment. The results of the equipment tests at our enterprise were taken as well. Our comparison was made on the basis of all of the data available. The first method where we are going to consider is HAV. As we already said before, the drying process involves cyclic heating plus vacuuming, with the subsequent increase in temperature and rise of vacuum level inside the chamber. The heating process uses the power supply to ensure the operation of heating plates inside the chamber, as well as the drive for circulation fans. After that, the heating system is disengaged and the vacuum unit is engaged, which requires power for the vacuum pumps and the cooling system. This procedure is repeated for a certain number of cycles based on the drying technology. You can see on the table the data of drying the winding in a vacuum over using the HAV method. We see the number of cycles totaling 5. We also see the power consumption within the cycle for vacuuming and heating. In total, it took us 8,850 kilowatts of power to dry the winding and 10 days of the process duration. We will compare these results later. Now, let's focus on the same vacuum oven, only in combination with the LFH heating system. The difference in operation is that we will heat the windings concurrently in a combination of two heating systems. That will speed up the heating process. Further down the line, after the first cycle, we will maintain the winding temperature by means of the low-frequency heating system. That will reduce the number and time of activations of the electric plate heating system. This table contains the data of drying the winding in a vacuum oven using the HAV plus LFH method. We see the number of cycles totaling 2. We also see the power consumption within the cycle for vacuuming and heating. it's hard to avoid noticing that the number of cycles has considerably decreased. There is only one first preheating cycle. Next, the vacuuming and heating process occurs on a concurrent basis throughout the remaining time. In total, it took us 3,265 kilowatts of power to dry the winding and 5.5 days of the process duration. Now, let's compare the data we have obtained. We clearly see the total results. In comparison, we see that the results have halved in the terms of time and energy consumption. We also note that when drying the small windings, it is possible to use only one LFH system. It should be concluded that completing the package with a system of heating through low-frequency currents had a positive effect on saving the time and money associated with repair or maintenance of the transformer. And now for the most interesting part. Tim, chief of our testing department, he will show you the equipment that we have talked about all of our presentation. Please hold as we are currently connecting to him. Hello, Tim. Take it away.
I'm Tim, and now I'm going to represent you our units. This is LFH unit and the vacuum oven. So let's start from the vacuum oven. What is it like? First of all, the oven itself, then the loading, unloading system, and the vacuum. Let's make a short review of the vacuum system. So you can see the piping coming from the oven, moving off directly to the booster. This is the roof pump, vacuum pump. After that, the material goes to the condenser or temperature exchanger. And for operation of the booster, we also use two vacuum pumps. These are rotary vane pumps with capacity of 100 cubic meters each. For operation of the valve, the system has the compressor. With the help of compressed air, we move all the valves on the unit. Besides, we have the cooling system. There is a chiller, and it enables to condensate extracted moisture into the tank or condensed material. So, piping from the oven, booster, temperature exchanger, chiller, and the system for condensation. It was about the vacuum system. Now, about the oven, I'm gonna open the door right now. At first, the pneumatic cylinder release the door. After that, 10 seconds delay, door goes. Now it's completely open. Let's see what is inside in here. Volume of the camera is 10 cubic meters. So that side is 2.2 for 2.5 meters. So altogether it's 10 cubic meters in power. We have two wings of the heaters. The total capacity is 45 kilowatts. And we also have tunnels for so loading and unloading system. We have the rail and the platform. Put down is leading, the other down is wheeling. So to activate the system, to play the heat like this. The transformer is placed on the leading platform. And with help of this button, we can move the platform inside the oven. Or we can move it along the oven. Okay. Heat it up. I want to close the doors. We open them automatically. So this is the screen for operating the door. It can be moved easily just by pressing the button. Door 12. The cylinder. This is the door 12. Now about the control panel. Yeah, it has the screen for operation of the door, and the main screen looks like this. We can see the complete installation scheme with all the sensors, pumps, and heaters and fans. So it can be controlled manually, like this. I have started the fan right now, the other fan. So these are the fans for internal circulation inside the oven. We have the fan to change actually the media inside the oven after the heating cycle. When the heating is completed, the extracted moisture is evacuated by opening the valve for air inlet inside the oven, and then the material is removed. So it was about the fans inside the oven. So here we can see the booster, vacuum pumps, temperature exchanger, the tank for collection of condensate, and a chiller. All the settings are made in this menu. I mean the temperature and the time of draining periods. The automatic mode is set in here. So at every step, we set the value of vacuum and temperature to be reached, then the time when the system is keeping the parameter, and when the moisture is extracted. After each step, we remove the extracted media enriched with water by opening the air inlet valve and by turning on the extracting fan. And after that, the system to perform the next step. The next step at the highest temperature and the highest value of the vacuum. Altogether, the system is supposed to perform 6 automatic steps with the different time, temperature, and vacuum value. Just to show you the valve for air inlet. It is over there. The air goes through the filter inside the oven and then is extracted by the fan. Okay, briefly, this is about the vacuum oven. We have 2 machines in here, and this is to demonstrate the principal possibility of their combined operation. If the heating in the separate system, like vacuum oven, is supposed to be placed inside the oven, we can arrange the heating directly the windings of the transformer using the low frequency heater. So let's go here. Start from this. So it looks like this. What you can see in here, we have the ports for connection of the main power. Then we have the ports to connect the cables from the low frequency heater to the windings, high voltage windings of the transformer. We have the ports to connect the system, to connect to the transformer, to connect the system to the transformer in order to control the resistance of the windings. And we also have 2 ports for temperature sensors. One is as rule inside the transformer, and the other one is based on its surface. So to combine these units, we need to provide connection from the low frequency heater to the hermetic ports of the oven. It looks like this. I want to note that these units are actually separated because each of the units is the complete system. But the principal possibility of combined operation consists in connection of power from the low frequency heater to the ports of the oven directly to the windings of the transformer. Now, about the low frequency heater. This system goes to South America. That's why we have the auto transformer inside to provide the proper voltage. It is of 220 volts. The part of the unit is the inverter, which provides the proper mode of heating. It is from 10 volts. So this is the main part. I mean, the power supply device. You can see the compartment of the unit. It is completely filled. So it's supposed to be operated in different climatic conditions. In here, we can see the compartment for storing all the cables. The cables are quite long, and it should provide the total power of the unit, which is 150 kilowatts. So the compartment for keeping the cable. We can also see it from this side. And the control cabinet. Again, we have here a schematic diagram of the system. We can see the parameters of the process, like temperature, winding resistance, current set point. We have the menu for making the settings. It is about the temperature and current set point. It is taken from the parameters of the transformer. Then the coefficients depending on the type of the operation provided, because this system can work in combination with the vacuum system, which is actually it takes place in this scheme. So particularly this LFH module is supposed to work with the client's vacuum system. So low frequency heater provides the heating of the windings, and the vacuum system of the client provide the removing of extracted moisture. Once again, this unit is supposed to work with the client's vacuum system. Just to say that the system also can be used in the combination with oil drying unit. And this coefficient is dependent on the type of combination. And in here we set the heating frequency, heating type, and number of cycles. As soon as these parameters are set, the system works out the heating mode by itself and performs it automatically. In changing the cycles, the one cycle is the heating, the other one, the following step is the defining of the temperature of windings coming on from the data of resistance which are measured. So it works in consequent steps. First, the heating. The following is the measuring of resistance and defining the temperature of the winding. And after this step, the next step of heating follows. So it was about the low frequency system. So in fact, I have shown the things I wanted to do. So please answer questions. We'll try to answer it.
So, thank you all for joining us here today. Thank you for asking your questions in the chat. You will receive the this presentation afterwards. We thank you all for your time, and I hope that you have a good rest of your day. Thank you for joining.